Let's look at a very simple structure. We have a straight beam with length of L and given cross-sectional area. One end of this beam is fixed. The other end is subjected to a vertical force F, and we can analyze the internal shear force and bending moment in this beam. We first determine the support reactions at the fixed support. We have a force and a bending moment. And if we choose this to be our x-axis, as we usually do, we can sketch the internal shear force diagram and the bending moment diagram. And if we decide to analyze a segment at an arbitrary position x, and the segment has a thickness of dx, according to our bending moment diagram, on the left-hand side, its bending moment is mx, and on the right-hand side, its bending moment is mx plus dm. Therefore, as you can see, the bending moment is not the same on the left and right side of this segment. And since we have already learned the flexure formula, we can determine the normal stress distribution on both left and right sides of this segment. The bending stress distribution is demonstrated here in both 3D view and profile view. As you can see, the bending stress distribution is different on two sides of this segment because the internal bending moment changes with x. Now, if we integrate this part of the bending stress, we get a force Fx. If we integrate this part of the bending stress, we get a force with the same magnitude Fx but opposite direction. The two forces cancel each other out in magnitude, but they create a pure couple moment that should equal to the bending moment mx at this location. Similarly, if we integrate this part of the bending stress, we get a force Fx plus dx. If we integrate this part of the bending stress, we get another force with the same magnitude, opposite direction. These two forces cancel each other out in magnitude. Therefore, they create a pure couple moment that equals to the bending moment at this location. And the resultant force along the x direction is still 0. This is all agreeing to our previous analysis. However, what happens if we section this segment horizontally like this and only analyze the top segment? So if we isolate this top segment, as a result, the remaining forces on the two sides of this segment no longer equal to each other. Therefore, in order to achieve equilibrium, it means that extra force must develop here at the bottom of this segment. That corresponds to shear stress here at the bottom. And if we assume this shear stress follows a uniform distribution, this delta F equals to tau times the area of the bottom, which equals to tau times t, the width of this segment here, times t dx. Therefore, we can write the force equilibrium equation along the x direction for this top segment, and sigma, the normal stress caused by bending moment at any given position y, can be determined by this flexure formula. We substitute that in, and we're trying to solve for tau to be 1 over it dm dx times the integration term. Now, here, t is the width of this top segment, and I is the moment of inertia of this entire cross-section about the z-axis. Since, if you recall, this I term comes from the flexure formula, and in the flexure formula, I is the moment of inertia of this entire cross-section. If you recall, the derivative of bending moment is simply the shear force, dm dx equals to v. For this integration term, if you remember this formula that we can use to determine the centroidal position of this shadowed area, therefore, this integration term simply equals to y bar prime times a prime being the area of this top segment, and y bar prime being the position of the centroidal location of this shadowed area to the z-axis. And we call it q, the static moment of an area. It has the unit of length to the third power. Therefore, from here, we can determine tau to be VQ over IT. And this is known as the shear formula. It is important to notice that for a given cross-section, V and I are both constants. V is the internal shear force at that location, and I is the moment of inertia of the entire cross-section about the z-axis. However, Q and T, they both change with vertical location y. Q, again, the static moment of an area, and T being the width of the top segment. So for this top segment that we just did analysis on, if we focus on a small differential element here and zoom in on this element, according to our previous analysis, shear stress develops at the bottom of this element. The magnitude is determined by the shear formula to be VQ over IT. However, we learned about the complementary property of shear. If shear stress develops on this side, it must develop on the other three sides as well with the same magnitude. Therefore, if we assume shear stress distribution is uniform along the z-axis, then here at this vertical location, shear stress develops like this. Therefore, we can apply the method of sections multiple times and apply the shear formula multiple times and determine the shear stress distribution on this cross-sectional area. The integration of shear stress over this cross-sectional area should equal to the internal shear force V at this location. As you can see, according to our analysis, shear stress varies with x and y coordinates, but it follows a uniform distribution along the z-axis. However, in reality, shear stress varies with z as well. Which leads us to the limitations of the shear formula. First, as I mentioned already, the shear formula only counts for the shear stress variation along the x and y direction. It does not count for the shear stress distribution along the z-axis. Secondly, it works better for long and slim section. It doesn't work as well for short and fat section. For example, for a wide flange beam or an I-beam, the shear formula gives better prediction for the web than the flange. However, that is acceptable because most of the time we are only interested in the maximum shear stress, and the maximum shear stress does occur at the web section of the beam. And thirdly, the shear formula does not count for the direction change of the shear stress at an angled boundary. For example, according to the shear formula, the shear stress distribution looks like this, when in fact, the shear stress should be along the boundary. Let's look at this example. We need to determine the shear stress distribution for this rectangular cross-sectional area subjected to internal shear force V. This is a very important example because later on, many cross-sectional areas that we are going to work with can be considered as composite areas made up of different types of rectangles. And also, before we start, let me remind you that we learned before how to determine the average shear stress to be the shear force over the cross-sectional area A, in this case, V over BH. Let's remember this and compare this to our conclusion after we have worked this problem out. Let me remind you again, in the shear formula, I is the moment of inertia of the entire cross-sectional area about the z-axis. And for a rectangle, it is 1 over 12 times b times h to the third power. Then we pick an arbitrary vertical location y for our analysis and pick the top segment. If you recall the principle of method of section, it actually does not matter if you pick the top segment or bottom segment for your analysis, and I will leave it to you to prove that. And for this shadowed area, since it is also a rectangle, its centroid location is right here in the middle with a distance of y bar prime from the z-axis, and we can determine that through our knowledge of geometry. And we also need the area of this shadowed area, and Q equals to y bar prime times a prime. Recognize that T, the thickness of this section is simply B. Substitute that into the shear formula. We can get tau equals to this. And as you can see, it is a function of y. It is actually a quadratic function of y, which indicates that its graph should be a parabola. And we can plot the shear stress distribution as a function of y. Unlike the linear distribution of the normal bending stress, the shear stress does not follow a linear distribution, but instead it has a parabola shape. At the two edges, the shear stress is 0, and at the centroidal location of this area, y equals to 0, we will have the maximum shear stress, which equals to 1.5 times the average shear stress. And also, we can integrate the shear stress across the entire cross-sectional area, and it indeed equals to V, the internal shear force at this cross-sectional area. Let's look at this example. I have shown a similar example before and determined the absolute maximum bending stress in this beam. And now we need to determine the absolute maximum shear stress in the beam and stretch the shear stress distribution at that cross-sectional area where that occurs. Once again, we start with the force analysis of this structure, and we want to sketch the internal shear force and bending moment diagrams, which I did already in the previous video. And from the internal shear force diagram, we can determine that the absolute maximum shear force in this beam is 405 pounds. From the previous video, we also determined the centroidal location of this cross-sectional area, as well as the moment of inertia of this entire cross-sectional area about its centroidal z-axis. Now, we need to determine the maximum shear stress, and based on our previous analysis, the maximum shear stress occurs on the centroidal axis, the z-axis. Therefore, we pick the bottom segment for our analysis to determine the maximum shear stress. You can also pick the top segment, and again, I will leave it to you to show that you will get the same result. And for this shadowed area, we need to determine its own centroidal location and calculate the Q, substitute into this shear formula to determine the maximum shear stress. And we can also use the similar approach to calculate the shear stress at these 2 points that are at the place where the cross-section area changes. They are right next to each other. However, point A is on the flange and point B is on the web. And we can calculate their shear stress. And based on all this information, we can sketch the shear stress distribution on this cross-sectional area as a function of position Y.